Hey, Pre-Cal 12, let's get after it. Here we go, video on graphing polynomials. So in the video previous to this, video 11, we learned all about basics of polynomials, and we kind of had a bit of a throwback look at linear equations and parabolas that we looked at throughout grade 9 and 10. But how that ties into this is I want you to consider behaviors of polynomials of varying degrees. So first degree polynomial is this, right? It has one factor. This is your classic sort of slope-intercept form. We have a root here at, let me go to white here. We have a root here at x equals a. So in this case, it's right here on my graph. But if we have a one exponent, right? If it's linear, we have what's called multiplicity of one. We cross the graph at one point. So if you have an odd but only a 1, you're going to cross through the graph. It's going to look slightly different as that exponent increases. So 3s, 5s, 7s with respect to odds, and then we'll look at evens here in a minute. But a 1 multiplicity root means we cross through the x-axis, just a straight, easy cross. Now, if you have even multiplicity, we are not only going to be a root, but we're not going to cross through the graph. We're going to do what we call bouncing. I call it bounces off the graph. So if you look at the graph here, this is basically a graph of our parabola, right? And if you remember a basic parabola, it was y equals x squared. And x squared is an even degree, right? Degree 2. Now in this case, our a value would be represented by that value there, which would be 1, 2, 3. So we get x plus 3 squared, because when x is negative 3, that's where our root exists. But when we have an even multiplicity, we're not crossing through the graph, we're bouncing off it. And remember that the work about the leading coefficient will change our end behavior. So in this case, we are looking at this one because it's positive leading coefficient. We start up and end up. If we were to look at this one and graph it, it would be a graph that starts down, it still bounces off the x-axis and finishes down. So anytime you have even multiplicity, you are not going to cross through the graph. Now, as I mentioned, if your multiplicity moves up from 1, moves into odd numbers, 3, 5, 7, so on and so forth, it's still going to cross through, but particularly when you graph these things in Desmos, it kind of makes it look like your graph is lying down on the x-axis a little bit, and that maybe you have multiple roots. You don't have multiple roots. Desmos does that to demonstrate that it is a root with higher than 1 multiplicity, but that is, in this case, even or odd, because it is passing through the graph. And you'll see what I mean when we pull up like a power 4 graph after the fact. And again, leading coefficient here, positive, means we start down and we finish up. And if we were to have a leading coefficient of negative, well, that just changes the behavior of my graph. I'm going to graph it here in black. It would start up, it would cross again, it would kind of lie on my x-axis and then work its way down. So that's sort of the Desmos shape. Doesn't mean we have multiple roots there. It means you have one root there. It's just of higher multiplicity. Now, steps for graphing is we want to take everything we've learned into consideration. Our x-intercepts, our y-intercepts, the general shape at those intercepts. So do we cross through? Do we bounce off? Do we lie a little bit on it? So it depends on the leading coefficient and the degree for our end behavior. And then we talked about our turning points. So a number of turning points as well. And then in this class, we're just going to draw sort of a smooth line. We're going to try and find some values in between our roots to gauge the peak height or peak depth. And then we're just going to roughly sketch our graph. We're not going to get too exact in many instances here. You'll see when you take calculus that you get some tools to do that. So let's graph this. Now, the first thing you want to look at is it helps to make sure that all of these roots are written in an order we're comfortable with and we're used to, where we have our x value first, right? Now, here we just have x squared. Here, yep, we have that, but here we do not. This is backwards, and it's actually going to make an effect on my leading coefficient. So let's change that. We're going to rewrite this so that we have x squared and then it's negative x plus 3. So just rearrange the order, and then x squared plus 1. Now, the reason why this matters is because we're actually going to factor out the negative in front of the x. And that negative is going to make its way all the way to the front, because now we have x minus 3, and then x squared plus 1. Because now we can access our roots. Where are our roots? Well, this is not a real root. There's no way you can make that equal 0. Because if you consider you're trying to solve this, it's not going to happen, because you have x squared equals negative 1, which means x equals the square root of negative 1, and that is not a real number. So we disregard that one, and here we're going to have a root. And the exponent on that factor is a 1, so we're going to cross directly through there. And that root exists at x equals 3. Watch the scale on this graph. X equals 3 is right here. The next thing we're going to look at is this x squared here, and that is a root at x equals 0, but it is of multiplicity 2. So we're going to be bouncing off that point. And then factoring out that negative gives us a negative leading coefficient, which is going to affect our end behavior. Now, if we were to multiply all of these things together, we have an x squared value, an x squared value, and an x to the power 1 value. And if you combine all of those leading terms, you're going to get an x to the power of 5 polynomial. So that means we have a x to the power 5, which is odd, and then negative leading coefficient. So it's going to take the same shape as a y equals negative x would take. So it's going to start up and it's going to finish down. So that's just our end behavior. Because now looking at our 2 points, we need to make sure that those 2 points connect, but we start up and finish down. So how are we going to make this work? We need to pick some points and kind of see what's going to happen. So here we go. The important point to consider is your x squared value, or your root at 0. We're bouncing off there. And if we're going to finish down, well, that means we're going to have to come through here and finish down. We know that that's going to happen because we know that we're also passing through the graph at x equals 3. And we know that here we are going to have to somehow get back to this point. So we're going to be up here somewhere, we're going to loop back around, and we're going to have to come down here. But we know we're bouncing off there as well because that's what's given, and our line has to shoot up because we're not coming back down. And this is why this is just going to be a rough estimate, because in your notes, I've made a table of values, but I just want you to be able to kind of roughly sketch this as well. If you know that you're starting up and you have to come down to this root and that you're bouncing off this root, you know that that general shape's going to happen. Now, do we know how high we're going to go around here? No. So that is when you pick points. So I'm going to erase some of this info down here. You would pick a point for x and solve for its output, solve for its y. So at this point, you would take this equation, and if you look at your grid, maybe try 2, because if x is 2, we should be working our way either to our peak or working our way back down. So if x is 2, you're going to have negative 1 times 2 squared times 2 minus 3 times 2 squared plus 1, which is negative 1 times 4 times negative 1 times 5. So you see you get negative cancels negative, you get 20. So when x is 2, your y value is 20. And then from there, so on our grid, it's about there. From there, you could check subtly on either side and see if you continue to go up or if you're already on your way down. But that's really enough to get a rough sketch. You know you're going to head up here, and then we are going to have to turn and come back down. So that's a rough sketch of what your graph should look like, and that is roughly what it does look like. You can always plug this equation into Desmos and see what the graph looks like. Just beware of the scale in Desmos when you're looking at it. You can play around with that window. So that's step 1. Find your roots, get your leading coefficient, get your degree, then consider what's happening at your roots, and then also your end behavior, because it'll help you kind of line up your path. So let's look at another one. Again, we have an issue with this value here. It is not in the order we prefer. We would rather see it in negative x plus 1. But in this case, we're going to have a similar scenario occur. We're going to have to factor out that negative. So you're going to have x minus 2, you're going to factor out the negative 1, and you're going to have x minus 1, and then x plus 1 squared. So just for the sake of notation, we like to write our negative at the very front. So that's going to give us -1, x minus 2, x minus 1, x plus 1 squared. Now let's look first at negative leading coefficient, but that doesn't tell us anything until we know the degree. So we have a degree 2 factor at the back, then a degree 1, degree 1. Total up those degrees, what do you get? You get a full degree 4, which means degree 4 and a negative leading coefficient, we are going to start and finish in the same direction, down. Now degree 4 also gives us our minimum number of turning points. We are going to have 3 turning points. And then from there, we'll start, and then we can consider x-intercepts, y-intercepts. Well, we know our x-intercepts, we can consider our y-intercept to see if we can find that as well. So first, let's plot our roots. So x minus 2 means we have a point at x equals 2. X minus 1 means we have a point at x equals 1. And again, watch the scale of the grid here. And now x plus 1 means we have a point at x equals -1, but it's squared. So it tells us there we're going to be bouncing off. Now we also know we're going to start down and finish down, so we can already say that this point is going to have to come up and then bounce off here. And now we don't know where we're going yet. So if you consider you got to cross the y-axis to get to your next roots, let's calculate our y-intercept. And remember that our y-intercept occurs when x is 0. So take this equation and plug 0 in for x. So if we did that, we get -1 times -2 times -1 times 1 squared. So that's going to give us 1, 1, 1, 2. So 2, but the negative cancels, but the negative stays. So we have -2. So there's our y-intercept right down there. Now, are we going to go lower than that once we cross? We very well may, but remember this is a rough sketch. So we know we're going to have to turn back because we have to get up to this next root. We know we're going through this root, and then we know we're going to have to turn back around to go through that root. That is the basic shape. Now, the only thing I estimated would be that point. Where's my peak going to be? So in order to get that peak, you could pick a value in between 1 and 2, say 1.5, plug that into your graph and solve for y. But for this example, I'm happy here. This is just a rough idea of what your graph will look like, and that is in fact the shape. And it started by getting the degree, the negative leading coefficient, the number of turning points, and our y-intercept, right? And if we look, number of turning points, 1, 2, 3. So boom, we're comfortable, we're feeling pretty good. So let's look at one more. This graph, we have, let's do our degree first this time. We have a degree 3 root, we have a degree 2 root, and we have a degree 1 root, which means we're going to have a 6th degree graph. If we have a 6th degree graph, it means we have 5 turning points, and it means we are going to start up and finish up, or start down and finish down. And if we look at our roots, we're in the right order, we're in the right order, we're in the right order. Our leading coefficient is positive, so that means we are going to start up and end up. So we know our graph's going to have that end behavior. What happens in the middle here is what we're going to figure out. So where do we have roots? We have roots at x equals 3, and that's a degree 1 root, so we're going to be crossing through. So you can already say, because are any of the roots further right of that? No. We have a root over here at -2, and we have a root here at +1. So if we know we're going to start up and end up, we can already add this feature. We know that's going to happen. Let me not jump too far. We just know that it's going to come down there and it's going to come down there. Now, if we look at the root x minus 3, that's a degree 1 root, so we actually know we're going to cross through that point. But if we look at the x plus 2 root, it's even powered, so we're actually bouncing off. So we know we're going to bounce off that one. So let's continue from there. Y-intercept would probably be the next helpful piece of advice. So the y-intercept occurs when x is 0, so that's going to give us -3 times 2 squared times -1 cubed. So -3 times 4 times -1, which gives us +12. So that's our y-intercept. You can see the scale of the grid gets all the way up to 40. And I've thrown the scale of that grid on there, which means I've crunched some other values. You kind of want to know what's going to happen in between this area here. So you would test a point, say x equals -1 in your equation, and see what y value it spits out. Because that'll tell you how high your graph goes. And from your notes, you'll see that it goes all the way up to 32. So you're going to get up to about here, and then it works its way down. You know you're going through the y-intercept. You know you're going through the root at x equals 1, and it's a cube root. So your graph's going to kind of lie on the line before it drops. And then the last thing you want to test again is, what's the behavior down here? So again, you could try x equals 2, good place to go. If you look at the notes again, I have found the values when x is 2, we are at negative 16. So we have a point kind of there. And then when x is 2.5, we're all the way down at negative 34. So we're down sort of here. So you know this graph is going to follow itself down here, flip up, and hit back to our graph because it needs to finish up. Now that's not a smooth curve, so let me just tidy that up a bit. 2 was at negative 16, and then negative 34, there-ish. So this one's coming down rather steep. It's going to turn there, it's going to work its way up, whoa, it's going to work its way up, and then it's going to go through our cube root point at 1. So there's a rough sketch of your graph. Again, you can see it produced in the notes, but it's helpful to test the points to find your peaks and your valleys. When we get to calculus, again, we will find ways to find those peaks and valleys in a relatively quick and very accurate manner. So that is graphing our polynomials. Now, moving from there, we want to be able to write the equation of a polynomial given either a graph or given information about its roots. So in this case, we have to make the connection that these are roots. These are solutions, those are x-intercepts. So what that means is, what does their factor look like? Roots have factor notation like this. If the root is -1, it's x plus 1, because this root tells us that x is equal to -1. And in this statement, when x is equal to -1, we have a root of 0 because we want to know when y is 0, right? So we have that root, but we have it twice. We have x minus 2, and that's for this one. And then when you have 0 for a root, you just have an x in front, because when that thing's 0, the whole thing's 0. So that's the root expansion of our equation. What we don't know, though, is there an a value in front of my equation? So how do we find this out? We find this out the same way we solved for a point on a line in grade 9. We were given an x value with a corresponding y value. So we plug the y value in for y, and that y value is that y value when x is 1. So we sub 1 in for x, and then we do a little bit of arithmetic and then a little bit of algebra to solve for our a value. So we end up here with a times -4, so a equals -5 over 4. Once we get that a value, we plug it in. Our unknown polynomial is -5 over 4 x times x plus 1 squared times x minus 2. So that is how we solve for a value to get the equation of our polynomial. Now, what about taking it from a graph then? Okay, well, from the graph, we need to kind of take all that knowledge we learned when graphing them to reverse engineering that. And it always starts with your roots, because here we have a root, and this passes right through. So that means we have a root at x plus 4, and it's degree 1. Here we have another root, and it bounces off. So we have x plus 2, but to the power of 2. And the reason why this is asking for the lowest degree is because we don't know if that's a degree 4 or a degree 6 root. We just assume it's lowest degree for this case because since it bounces off, we know it has to be even, so we say it's degree 1. If we had an odd pass-through and it kind of lay on the graph a little bit, we would assume 3 instead of 5. But these ones pass straight through at x equals -4, and then again here at x equals +1. So we just assume they are power 1. So those are our roots. And then what is our a value? Well, in this case, you are given a point here where we can see that our y-intercept is 0, -3. So that's the point we use to solve this portion of our equation. So when y is equal to -3, x is equal to 0. So we're going to do a little bit of arithmetic here again, and then we are going to solve for a. So negative 3 equals a times 4 times 4 times negative 1. So negative 3 equals a times negative 16. So a equals 3 over 16. So we get an a value, which we can then plug up here. Rather than rewrite the whole equation, we can just rewrite or delete our a value and write in the solution, 3 over 16. And that is the equation of that polynomial in its lowest degree. So, last one. What we have here is we're determining the equation of a polynomial given abstract parameters. We're given the parameters that we have these roots, x minus a, x minus b squared, and x minus c. And what you're given though is you're given that a is less than b is less than 0. So that means it doesn't matter where you want to do it on here. For the sake of the graph, I'm going to plot this here, and I'm going to call that a, and I'm going to plot this here, I'm going to call that b. You could plot them anywhere on the left side of the grid, just as long as a is more left and b is left of the origin because it is negative. And then we're given c is positive, so again, you can put that anywhere you want. Let's put it right there, as long as it's in that side of the grid. So from there, what do we know? We know b is squared, which means b is going to bounce off. And then we also know that a and c pass through. We know the total degree is 4, and the leading coefficient is a positive value. So that means we're going to start up and finish up, which means, what do we know? We know that we're coming down from here. We have to get back to that b. We bounce off at b. We go through the y-intercept somewhere, and then we have to go back up through c. That would just be a representation of that scenario. Now, how do we determine, or how can we check that our y-intercept is in fact negative? Remember that your y-intercept occurs when x is 0. So what you would have in this case is you would have negative a times negative b squared times negative c. And now, a lot of people rush to multiply these together and say, well, all the negatives are going to cancel because negative b squared is just b, and negative c squared times negative c times negative a, well, the negatives cancel. But herein lies so you should have a positive y-intercept. But herein lies a subtlety. The subtlety is that a and b are both negative numbers. So if you have negative a, that negative has nothing to do with the a. That actually means negative 1 times a. And then the negative in front of the b means negative 1 times b, right? It just makes whatever number gets inserted in there negative. Now, again, this isn't going to matter either way because it's squared, so that's always is going to be positive. But since we have negative 1 times a, and a is given to us as a negative number, this is actually a positive value for a when x is 0. And then for c, it's the opposite. We know that c is a positive number, so you just have a negative times a positive number, so c stays negative. And in there you see that you get a product of negative a b squared c. So now that has to be a negative value. And that's why we cross in the negative realm of our y. So that's our video on graphing polynomials. Moving forward, we're going to get into long division and synthetic division, which helps us break down higher degree polynomials, hopefully into quadratics, so we can fully factor them and then graph them. So it all gets connected. Thank you so much, and I will see you next time.